So here's the claim that the idealized change of the area of the rectangle is just the sum of the pink and the green, which is dw times h plus w times dh, and in the limit, which is always what we're interested in deriving a rule about derivatives, we can ignore this super tiny area. It's a great example of the power of calculus to simplify what would otherwise be a complicated calculation. And so one more numerical example to show just how small that error gets. One more time with w equals 5, h equals 3. Let's say, and I'm not going to put this on the GeoGebra because it's just going to be invisible. dw, say, was 0.001. dh is 0.002. The pink is going to be 0.003. The green is going to be 0.01. The brown, let me slide over a little bit, is going to be super tiny. And so dA is relatively simple. It's always following this pattern. And that is as simple as it's going to get, because that's really the rule we're going to, it's basically a form of the rule we're going to. And it's only off by this tiny, tiny amount. And I could make this smaller, and this smaller, and smaller, and smaller, and smaller, because if I'm looking for a derivative rule, that's what I'm supposed to do. And I'm supposed to take the limit as these changes go to 0, and see how the change in the product relates to the changes in the individual factors. So this is the core of the rule, but there's two versions I want to show you. Certainly the version that you'll usually see isn't about differentials, it's about derivatives, but it's so easy to derive it from this, okay? So I mentioned at the start, I was thinking of these all as functions of t, but then t hasn't shown up for quite a while, because I was just saying, suppose I just happen to know how much w has changed, and I know how much h has changed. Can I just tell you approximately how much w times h, the area, has changed? Well, now I just assume this is all happening in time dt. So I write down my formula, for the idealized change, and then I'm going to divide that by dt, and that's all I have to do. I literally just have to divide by dt. This is the power, part of the power of knowing the differentials, is that once you're clear on the differentials, if that all happened in 1 millisecond, then I just divide everything by 1 millisecond. This turns from how much the height changed to how fast the height is changing as a function of time. This changed from how much the width changed to how fast it's changing as a function of time. And this is how fast the area is changing. Again, I want to emphasize that all we've used, we haven't, even though we used the picture to get the intuition, all we've used really is that one quantity, A, is the product of two other quantities. This is a completely general rule, and this is the standard form of the product rule for derivatives. Anytime you have two quantities or two functions and you multiply them together, this is how you take the derivative, and I'll just write it explicitly, of those two things. So you'll often see, of course, with the letters f and g, that d by dt of the product of two functions, whatever the heck their formulas are, doesn't really matter. It's going to be d by dt of f of t, the derivative of the first. You can put in a lot of parentheses to make it really explicit, but you don't usually put these in, times the second, left alone, plus the first left alone, times the derivative of the second. Now you'll sometimes see this in other orders, because multiplication's commutative, addition's commutative. For here, it doesn't really matter. In later cases, it really does, so I tend to want to write it in exactly this way. So derivative of the first times the second left alone, plus the first left alone times the derivative of the second. It's not, absolutely not some arbitrary thing somebody just came up with. It's because that's how rates of changes of products have to work. And I would invite you to think about the pink and the green areas in justifying that. Now, there's a really cool form that you don't see very often, which I want to talk about a little bit, which is to focus on the relative change. So let me actually take it back to the sort of more chunky changes with really, really simple numbers. And I want to show you how pretty this is. It actually gets prettier when you don't focus on how much extra area you're adding and how much the width changed or how much the height changed. I want to say, in a percentage sense or in a relative sense, how much did I change this amount W? So let me just do the example here. Here, if I look at what would be called the relative change in W, and this is just like percentage error, things like that, things you've seen before. dW over W in this case, that's 0.5 over 5. That's 1/10, 10%. I'm just going to write it as 0.1. Okay. dH over H, by what proportion or percentage, or relatively speaking, how much did that change? Well, in the example I have set up here, 0.6 over 3, which is 0.2. And I don't have quite enough room. Okay. So let's see what dA over A was. Okay. Now remember, this is still ignoring the brown. Absolutely crucial that it's ignoring the brown, because in the limit, when these are D's and everything's differentials and sort of infinitesimal quantities, you can ignore the brown. You really can say it goes away. The dA over A, so that was the 1.5 plus 3, ignoring the 0.3, all over 15. All right, let's just calculate that out. 4.5 over 15, that's 0.3. That's kind of suggestive. And I claim it's not at all a coincidence that that is the sum of these two numbers. Because let's see how that calculation came up. The 1.5 was 0.5 times 3, plus the 3, the area of this green, was the 0.6 times 5. And then I'm dividing that by 3 times 5. Well, let's see. In the first one, if I just separate it out, the 3's cancel. Actually, let me separate it out. Let me just convince you I'm not doing partial cancellation. It's just really two fractions. I can just separate the numerator, which is always legal. People don't realize how useful this is because we focus so much on the complicated operation sometimes of combining of common denominator. Very often, the key step is actually to separate something that already has a common denominator into two fractions. Guess what? In this one, they cancel. That is dW over W. Here, the 5's cancel. That is dH over H. So, what this says is the percentage change, or the relative change in a product, is exactly just the sum of the relative changes of the factors. Now, that's kind of funky. It's really focusing on the fact that there's a sum here. Okay, so let me write it out. Not just do it verbally. The relative change in a product of two quantities is the sum of the relative changes of the factors. And now this is, to make this exact, it needs to be talking about the differentials. So really, the idealized approximate relative change. So it's not literally true for the actual relative change, but if you go ahead and ignore that brown rectangle and are okay with that approximation, then it's the sum of the relative changes of the two factors. That's really, really simple. That's actually my favorite version of the product rule. Let me just prove it for you just real quick. If you believe our derivation of the product rule before, if this was really dW times H plus W times dH all over, okay, so that was dA. What was A? Oh, it's just WH. It's just exactly the same calculation in general that I just showed you. In one of the factors, the H's cancel, and in one of the factors, the W's cancel. So let me show you a numerical example, something that doesn't have to do with rectangles. Okay, and something that I think is people find fairly plausible. Suppose I'm looking at like an economics example. The population of Albuquerque increases by 2% over some amount of time. And we could talk about that time and put in DTs and all that. We don't have to. And then let's suppose on average, the personal income of every person increases by 3%. To be really, really simplistic, suppose everybody has the same income. And in this time, everybody got 3% richer. And there were 2% more people from birth or immigration or something like that. And then I just want to know if I'm like a city manager or something like that, hey, the total tax base is sort of the total amount of income everybody has when we put it all together in one big pool and we could tax it. What's it going to increase by? Well, let me just show you the exact calculation and show you how, to a very good approximation, this rule works. It's going to be increased by a factor of 1.02 because that's the population increasing. But it's also going to get multiplied by 1.03 because everybody's getting that much richer. What happens if you multiply 1.02 times 1.03 and you use a tiny bit of algebra? I'm going to write that as 1 plus the change times 1 plus the change, and I'm going to FOIL it out. Look what I get. I get 1, okay, that's because that's what's already there, plus 0.02, plus 0.03, plus a very small number, 0.0006. Make that more visible. Okay. And so it's multiplied by a factor of 1 plus, so approximately, I'm going to ignore that very, very small factor, 1.05. Not what I wanted. There we go, that's better. Okay. So it's approximately 1.05. So the tax base has increased by very close to 5%, which was just the sum of those two numbers. Usually when I get people to guess this, they're pretty good. They sometimes will guess 6%, but if we do enough examples, they see that that can't be the right rule. It's not the product of those things. It's actually the sum. That if one quantity increases by 2%, the other increases by 3%, then to a very good approximation, the product of those two quantities will increase by 5%. So that's a very concrete use of this kind of idea of proportional change. And so this is right here. This is something that I often talk about in my classes as one way to think about the product rule. It's a little bit different from the standard way.